Increasing, decreasing functions. First derivative test for relative extrema. You guys know this stuff already, but we'll try to fly through it and get you some good practice on it. So this is on page 91 in your book. We're going to find domain restrictions. That's really important first because that can mess you up, right? If you use those values and forget about the restrictions, then you're going to run into wrong answers, essentially. Because those domain restrictions don't actually appear on the graph if we were looking at the graph, right? Because that's what we're talking about here. We're talking about graphs. Well, it's a visual representation of the function. So we want to find all the critical numbers, the critical values. The domain restrictions are not critical values. Then we want to make a little number line, and it doesn't have to be anything super fancy. We're going to see where the signs change, if they change, and from there we'll determine relative min or max. Okay. I've seen some places where they make tables instead. I don't prefer that. I don't know the way you were taught. Hopefully it was with number lines and pluses and minuses on. Oh, okay, perfect. And that's what we're doing, okay? One of the things I do want to mention is when they ask for the minimum or the maximum, it's those y values that determine what is the minimum of the function, the maximum of the function. Sometimes they'll ask for where does that occur, what point does it occur, or sometimes they will ask at what x value does the minimum or maximum occur. So be careful in terms of making sure that you're actually answering the question that is being asked. We can get tripped up a little bit there. This is from your AB book. Okay, I liked it better than one of the things that this workbook series doesn't have is a lot of explanation. The AB book is a better place for detailed explanation. And honestly, all the new material that we'll cover in the second semester is also in the AB book. So that's the other reason why we have it. Long story short, if the first derivative is positive, that's what this is saying, greater than 0, is positive on some given interval, then f is increasing. So not that the first derivative is increasing, the function f itself is increasing on that particular interval. If the first derivative is negative, then the function f itself is decreasing on that interval. Now I'm going to put some pictures up here that kind of illustrate that. And I would, for myself, I need to visualize something. Maybe you don't have to, but I do. Maybe you just memorize it and fine. But remember that the first derivative is the slope. So they're saying here, if the slope is positive, then the function f will be increasing. If the slope is negative, then it will be decreasing. And here's a good example, and this is from your AB book as well. Notice here that we look at tangent lines, right? These tangent lines are positive or negative here. Positive. The slope is positive, okay? The slope over here, negative, and the slope over here, positive. So if I was trying to decide where is it increasing, where is it decreasing, okay, all I have to do is look at the slope of the tangent lines. And so between A and B and between C and D, we have positive slopes of tangent lines, which means f is increasing. In between B and C, we have negative slopes of the tangent lines, which means it's decreasing. And that's essentially what it is. Okay. So that's how you can identify from a graph where it's increasing, whether or not that slope is positive or the slope is negative. And that's how this correlates to this test. This is also from the AB book. This is the first derivative test. So now what we do is we use the first derivative test to try to find and see if we can find a local maximum or a local minimum. And I have some clarification coming after this. No, I'm getting my days mixed up. My bad. No, I do not. Okay. So if the first derivative changes from positive to negative, all right, and we just saw an example of that on the last page. So the slope of the tangent lines are positive, and then it switches to negative, then I'm going to have a local maximum at C, or a relative maximum, same phrase, okay? If the first derivative, the slope of the tangent line, changes from negative to positive, then we have a minimum. And it is possible that we could have no sign change. This is what C is saying. There is no sign change. So if the first derivative of the slope of the tangent line is positive to the left and right, there's no sign change between the function at the critical value, or no negative sign change, okay, then there is no minimum or maximum at C, all right? What usually will happen in that case is that you will have a horizontal tangent, and so the slope goes to 0, but then it stays positive again. So it ends up being increasing for the entire function or decreasing for the entire function, even though that one little point, it's sort of nothing. It never decreases or it never increases. That's what we're talking about in this situation. And so here are some illustrations of that. Feel free to put those in if you want. But this is the exception. These are both C's, right? So this is increasing, positive, then it's 0, but it's still increasing. Okay, here it's decreasing, 0, but still decreasing. It never increases. Here there's an actual sign change. Positive to negative, negative to positive. That's the key. There has to be a sign change in order for the possibility of a minimum or a maximum to exist. Any questions about any of that? Hopefully that just reinforces some of the stuff you already know. All right, we're going to work through 2 examples today, and then you'll have the rest of the time to work on your own, okay? So here's the first example. These are going to be from your book, from your little workbook. Okay, so we're finding intervals on which these functions are increasing and decreasing, and then finding the local extrema points. I know it's smallish up here on the screen. I should find out which page it's on in your book. It's probably like 92, 91, 92. 92. Okay. So this is page 92. So if you wanted to screenshot it from there, then you can see it better. Do you want to work on it on your own, and then we'll come back and look, or do you want to work on it together? I will give you the option. You tell me. On your own. All right. So one of the first things that we should be doing with every function that we look at is trying to determine the domain and see if there are any restrictions that we need to account for as we move forward. So the first question that I would suggest that you ask for every single problem is, are there any restrictions? Is there anything that we can't allow X to be? So as we work through this, one of the things we should be thinking about is, all right, we have this 2/3 power. Which means we have a cube root. All right. Is there any number that can't be inside a cube root? No. It can be positive, it can be negative, right? Now, if this was a square root, we'd have to be a little more careful, right? Or a 4th root or 6th root or 8th root or something like that. But with an odd index, there's no restriction. We don't have to worry about it. The answer simply is no. X can be anything. What is under the cube root can be anything. So I don't have to really worry about that. But that is something that what will happen as you work through your problems, if you neglect to ask that question right off the bat, you may think that you have a critical number, and it's really not a critical number. You shouldn't be including it because it's not on the graph at all. All right? All right, so that's our first move. Then, of course, we need to find critical values, and that means I need to take the derivative. Now, if you took the derivative a little bit differently than me, that's okay. We should have got basically the same thing. Of course, chain rule requires me to take the derivative of x squared, and that's what the extra 2x is all about. All right, and so now the trick is setting these things equal to 0, figuring out what makes them 0, okay? This one is easy enough, right? What value for x is going to make this 0? 0. All right, how about here? Plus or minus 3. So if x squared is 9, then I get a 0 out of this. So those are my critical values. All plus or minus 3 and 0. And that's it. So from there, that's where we can make our number line and try to figure out where it's positive or negative. And so I just make I don't know if this is what you do. Is that what you did? Did you make a number line that looks like that? So I include all the values on it. And now I've got to start testing intervals and trying to figure out where I have positive values, where I have negative values, okay? Fortunately, and it depends. You can start in lots of different places to try to figure it out. I try to find the ones, to me, that are the easiest. And for me, the ones that are always the easiest are the ones like, where does this definitely have to be positive, right? When I'm dealing with cube roots and that kind of thing, when I plug in anything bigger than 3, right, this whole thing ends up being positive. And so I know for sure that I have a positive over here, okay? So I'm looking at the first derivative. And so if I'm bigger than 3, this has to be positive, which means this whole thing is positive. And then if I'm bigger than 3, this is positive. Where I start running into issues is down in here, because this is still positive, but what happens to this? When I'm between 0 and 3 here, what is x squared minus 9? Positive or negative? This is negative, right? So when I take the cube root, technically the cube root's in the denominator, but whatever, we're just talking about the sign. This whole thing is negative. So I know my next area is going to be negative. Now, one of the things you have to be careful of, because you could start thinking, okay, then the next one's positive, and the next one's negative. That doesn't always happen. And that example C of the rule that we looked at illustrated that. So you can't just assume that they're going to alternate, because they don't always alternate. They alternate a lot of the time, okay, but not always. So just be careful. All right. So when I plug a negative in here, now this term becomes negative. Okay. So this term now becomes negative, but if it's still in between 0 and negative 3, that means this whole thing is also negative. So this is a negative, this is a negative, of course, a negative times a negative is a positive, and then my last one, this still is negative, but now when this number here gets less than negative 3, the square of it gets bigger than 9, which turns this to positive. So a positive times a negative, that is a negative. I don't know how much work you have to show for any of that. I don't think you have to. I think you're allowed to just kind of type that in or do it in your head or whatever. But if you feel compelled to show the work, show the work. So then we need to find out the intervals and where they are increasing and decreasing, and find local extrema. All right, so this is something I keep hammering away with my Algebra 2 kids, is they don't read the directions. It's really important to make sure you're answering the question. So I'm going to start with increasing. All right. Well, it's increasing where the first derivative is positive. So I have two intervals where it is increasing. So it's increasing over negative 3 to 0 and 3 to infinity. Now, one of the things that I've learned over the last few weeks is that on a free response or even a multiple choice, they don't give a rip about the bracket or parenthesis. They don't get worked up about that. So if you didn't have it with brackets and you had them all with parentheses, it's okay. They're not going to care about that, and they won't put on a multiple choice. They won't give you one with brackets and then give you one with parentheses with the same number. They're not going to worry about that. Okay. And then of course it's decreasing over these two intervals. So from negative infinity to negative 3, and from 0 to 3. So that takes care of my increasing and decreasing. Now, what we have to decide is, where is there a maximum? Where is there a minimum, if there is one? Okay. So it's going to be either at here, and it asks for the points. Right? It asks for the points. So it doesn't want to know just where it doesn't want to know just where it occurs. They want to know the actual point that is a minimum or the actual point that is a maximum. So negative 3. What do we think? Is it going to be a minimum or a maximum? Negative to positive. This is a minimum. Positive to negative. Negative, so. Bless you, all right? So, for relative minimums, those are going to occur here from negative to positive, negative to positive, negative to positive. Okay, and we already determined, of course, when now for the minimum and maximum points, I'm using actually F. So, of course, when we plug plus or minus 3 in, this whole thing becomes 0. So I know that the corresponding y values are 0. And then when I plug 0 in here, I have negative 9 to the 2/3, which whatever that is. Okay, so my relative maximum, and I just left it negative 9 to the 2/3. So I have a maximum that occurs at 0, two relative minimums that occur at negative 3 and 3. It's a good question. When you're trying to figure this out, can you use your calculator? What I would say is, I think you should be able to do it without a calculator. And my answer, because I don't know for sure if that kind of question would be, a calculator would be allowed for that or not. I would say, obviously, if you can do it without a calculator, then you're fine either way. And I like it just for myself. To me, it's good practice. Of course, I'm out of practice. You guys are not. But I like doing some number theory and playing with that a little bit just to make sure that it makes sense to me. Okay, how many got all this? All right. Do you see where you were close? Okay. Or is there a significant thing? Is there a significant thing that we need to address?
No, I just didn't put the points at the end.
Okay.
I just put
Okay. For your points?
Yeah.
Yes. Okay, so that's a common thing. Like there's a lot going on here, and it's like, what are we conceptually trying to accomplish? And so when I'm creating my number line, we're trying to see the slope of the tangent lines. But then the points themselves are, none of this is on the graph. This is not the graph. This is what's happening to the graph. We're looking at a graph of this actual function. Okay, and so yeah, careful on that. All right, here's another one. This is number 5, so it's probably on page 93, would be my guess. Is it still on 92? All right, fine, still on 92. Okay. Same procedure. Give that a shot. Any restrictions? No restrictions. We don't have any fractions. We can plug anything in. It's fine. All right. So potential critical points. First derivative, 3x squared minus 6x plus 3. Then I'm gonna try to figure out what makes that 0. And so I factor because I like to factor. So 1. 1 is what's going to make that 0. Okay. So then I make my little number line. And what's going to happen here? Yeah, positive on both sides. Because no matter what you plug in here, even if this value is negative, it's going to get squared and it's going to be positive. So it's going to be positive on both sides. Okay, and there's this phrase that they use in this workbook that I wanted to show you that I'm going to get to. So we still can answer the question, though. What interval is it increasing? All of them. Okay, so how do we write that? Negative to infinity. Okay. Where is it decreasing? Yeah, never. It's never decreasing. So...
Do we have to write decreasing if we write increasing as negative infinity to infinity?
I think it's important to demonstrate that it's never decreasing, yes. Okay? It's not that it's... Here's the thing, and we looked at one before. It's technically not increasing when x equals 1, right? Because when x equals 1, the slope of the tangent line is 0. It's not doing anything. It's not increasing or decreasing, right? And so... technically, when we say that it increases over the whole thing, what we're really saying is that it never decreases. So there's kind of a technicality there. And so that's why I think that is important. It doesn't decrease at 0. It doesn't actually increase at 0. But what we say is, like, we don't want to get into the minutia of that. And so we just say it increases over the whole thing. But I do think it's important to point out that it actually never decreases. So, yes, I would like you to write that. All right. Last thing, extrema, we don't have any. Okay, there are no extrema. And this is the phrase he uses in the book that would be good to talk about. An example of something called a strictly monotonic function. I know, we just talked about that, and that's why I was like, that's a different way of using that word. So that's the verbiage that he uses in the book. I don't know why you would ever need to know this, but to me it was sort of an interesting, nerdy math fact. So I included it. And I also included this example because I want you to know and you guys already know this, that this will happen sometimes. Okay?